Alright, so today we are going to talk about the mole. So a lot of times when we say the mole, most people think moles on your skin or like the animal the mole. But the mole is a very important part of chemistry. It actually has its own day, October the 23rd we consider Mole Day, and that's because the mole is the center of our conversions between different elements and between different compounds and molecules. And so we use the mole as a representative number. And what I mean by representative number is like when we say 1 dozen, okay, we automatically think 12 of something. So you go to the grocery store and you pick up 1 dozen eggs, which means you're going to have 12 eggs. Just like 1 ream of paper is 500 sheets. And the reason why we use representative numbers is because they're easier to work with. Rather than saying, hey, I need 2,500 sheets of paper so I can make copies, I can say, hey, I need 5 reams of paper, and it's much easier to work with. So that's the same thing when it comes to the mole. 1 mole is equivalent to 6.02 times 10 to the 23rd of something. Okay, so usually when we're using this representative number, it's going to be of atoms or of formula units, which you will see me abbreviate as F units from here on out, and molecules. 1 mole can also represent either the mass of 1 element or the mass of an entire compound or molecule, and I'll explain that in just a minute. But this whole unit, or the mole unit, is used so that way we can simplify what we are looking at and what we are talking about. Excuse me. But first, before we dive into the mole and the conversions that we have, let's talk about formula mass. We talked about formula mass when we looked at percent composition. And remember, formula mass, this is just adding all masses from the periodic table of whatever element or whatever compound you're working with. So let's just say I wanted to know the formula mass of, let's see, phosphorus. Phosphorus's formula mass on your periodic table would be 30.97. So 30.97, and this is in grams. Well, now that we're looking at moles, I just told you 1 mole is equivalent to whatever the formula mass is. So formula mass is also equivalent to what we call molar mass. But molar mass, instead of just having grams as our unit, molar mass would have phosphorus as 30.97 grams per mole, which just says that for every 1 mole I have, I'm actually measuring out 30.97 grams of phosphorus. And so I can ask you the molar mass of pretty much anything. I can look at CO2, okay, and what you would do is you would find the mass of carbon on your periodic table, which is 12.01, and I would add it to oxygen's mass, which is 16, and I would have to multiply it by 2 because I have 2 atoms of oxygen present in CO2. And so when I do this, I get 44.01 grams for the formula mass, or grams per mole for my molar mass. And we can do this pretty much with anything we have. With that in mind, we're going to use formula mass to help us convert when we're using moles. The mole, I would say, it's a little bit selfish. It's the center of everything, okay? And because it's a representative number, I can use it to represent, let's say, atoms, which is used, or which is the unit used for just 1 element or diatomic elements. And we have molecules it also can represent, which are our covalent compounds, and then we have formula units, which represent our ionic compounds. So for us to go from the mole to any of these 3 units, I use Avogadro's number, which I've already shown you, which is 6.02 times 10 to the 23rd. And it's named Avogadro's number after Amadeo Avogadro. He's not the one who actually came up with this number, but they named it in his honor. So we know that 1 mole is equivalent to 6.02 times 10 to the 23rd. We can also use the mole to convert to grams. And we use our formula mass, or the periodic table, adding up all of my masses on my periodic table, to go from moles to grams and grams to moles. Okay? And notice that I can't go from atoms or molecules or formula units straight to grams. There's not a path right here. So what I have to do is I have to convert to moles first and then to grams. And we'll talk about that more in just a little bit. And then we can also use moles to go to liters, or to find volume, at STP. And STP means standard temperature and pressure. And so when we're looking at standard temperature and pressure, if you look at the back of your testing periodic table, or if you look in your notes, you will see that standard temperature is usually 0 degrees Celsius and pressure is considered 1 atmosphere. We are not going to get into too much detail about this. We'll talk about this more when we get to gas laws, but for now, just know that when you're solving for volume, if it says STP, you're going to use 1 mole equals 22.4 liters. Okay? So that being said, now we can actually work out some problems using this setup, and we can convert from moles to atoms, atoms to moles, atoms to grams, but we have a specific setup that we use using dimensional analysis. And remember, dimensional analysis is just setting up a bunch of factors or a bunch of relationships to get us from one unit to the next. So let's start off with one-step conversions. So I may have, let's say, 1 mole of carbon, and it says to determine the mass in grams. So I'm starting here, and I'm going to write here. So I have 8.0 moles, and make sure you write that 0 because we have to keep our significant figures when we are converting. And I'm going to put carbon right next to it. It's very important that you include your units and your element symbol, because when we get to stoichiometry in a few weeks, we are going to be actually canceling out not only the units, but also elements and compounds. So to go from moles to grams, I'm going to use the formula mass. So if I look on my periodic table, I know, and I'm going to do some scratch work over here, that 12.01 grams per 1 mole is carbon's molar mass, or 12.01 grams is its formula mass. So I'm going to use this relationship. I want grams, so I'm going to put grams on the top. Okay, and sometimes I write this as one big line and separate it by a vertical line. It doesn't matter which one you show, just know either you need to put a vertical line to represent multiplication, or you need to put the multiplication sign. So I know that I have 12.01 grams of carbon, and I'm going to grams, so that's what I put at the top, and I want to get rid of moles, so I'm going to put 1 mole at the bottom. And it's very important that you put all units, because then we can see, alright, moles are diagonal to each other, so I can cancel that out. I'm left with grams, or mass, which is what I wanted, so grams of carbon, and then from here you just plug it into your calculator. My suggestion is, if you're using one of the TI-30XS calculators, the newer ones, you will want to use this ND button, okay? Because we're not always going to be working with simple numbers, and you want to make sure you plug it in correctly. So I have 8 moles times the 12.01 grams of carbon, and then it's divided by everything on the bottom or in the denominator. So that was just 1 for this one. I hit enter, and I get 96.08. Okay, but this is not our final answer. We have to maintain significant figures, and your significant figures are focused or based off of what we started with in the beginning of the problem. So I have two significant figures here, so I have to report my answer in two significant figures. So the final answer you would circle or square would be 96 grams of carbon. Okay, so hopefully that's not too bad, remembering dimensional analysis and Algebra 1 problems. It's a very simple setup as long as you remember the conversions and where all of these numbers are coming from. So let's pull another simple one-step problem between mass and grams. Let's look at number 5 on our unit sheet. So we have 0.750 moles of oxygen, and we want to know how many grams that is. So I know I'm going from moles to grams, so I just have one step using my periodic table. Well, I can see on my periodic table that oxygen has a 16 grams of atomic mass, and you're going to have to excuse the intercom. It keeps on going off here at school. I'll try to pause as much as possible so you don't hear the crazy. But anyways, we have oxygen, which has a mass of 16, but notice oxygen is diatomic, and so remember our diatomic molecules naturally pair up into twos in nature, and so that's our hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So if we're working with just one of our diatomic elements, we have to include both atoms. So 16 times 2 is actually going to be 32 grams of oxygen that we're going to be using, and that's per 1 mole of oxygen. Okay? And so from there, our moles cancel out, and we are left with grams, which is what we want. So I'm going to come back to my calculator. I'm going to hit that ND button, and I'm going to do 0.750 times 32. Divided by 1, and it gives us 24. So even though it gives us two significant figures, I see I have three significant figures in the beginning, so you must add a 0.0 at the end to maintain significant figures. Okay? So my suggestion for you is to take a moment and look at Part B of your unit sheet and do any of these problems, or pause the video and use this sheet as practice and do these two sections. Those are one-step conversions between mass and moles. So here we're going from moles to grams, and then down here it's just going backwards, grams to moles. And so just in case you feel like going backwards is going to be a little bit difficult, let's do 280 grams of iron, and it wants moles. So what I'm going to do is I want to cancel out grams, so I'm going to put grams at the bottom now instead of at the top, and I'll put 1 mole at the top because I want moles of iron. And from there, I just pull the mass of iron off the periodic table, which is 55.85, and then grams will cancel out. And so now I'm going to hit the ND button, and I'm going to put 280 at the top times 1, and it's going to be divided by the 55.85 grams of iron, and that gives me 5.0. And so I have two significant figures here because this trailing 0 does not count because there's no decimal place present. So 5.0 is my two significant figures, moles of iron. And see how 5 moles is easier to work with than 280 grams of iron. Okay? So that being said, if you need more practice, go back, look at your unit sheet, and do these two sections of Part B. But I'm going to move on to our other one-step problems. So let's see if we looked at, say, going from moles to atoms or atoms to moles. Right, section 3 of my unit sheet right here, I have 80 moles of methane, and it wants me to go to molecules. And then I'm going to come up here, and I'm also going to do 8.1 moles of gold going to atoms. And see, these are technically the same conversions, but we use different units because atoms is focused on one element, molecules is focused on covalent compounds. Okay, and of course formula units are focused on ionic compounds. I don't have any examples here, but it's the same process that we're using. so let's look at 80 moles of methane. Alright, so if I am going to molecules, I know that our flowchart on the previous page showed that I can use Avogadro's number. So I can use 1 mole, and I'm going to put moles at the bottom to cancel it out, of CH4 is equivalent to 6.02 times 10 to the 23rd. And this is going to be molecules because we are working with a covalent compound right here. So moles are going to cancel out, and I'm just going to plug it into my calculator. Right, so I have 80 moles times, and make sure you always put anything in scientific notation in parentheses over here so that way it reads it correctly. 6.02 times 10 to the 23rd. Be sure to hit the right arrow to bring it out of the exponent and close parentheses. Divide it by 1, and you're left with 4.816 times 10 to the 25th, but I only had one significant figure here, so I'm going to round up to 5 times 10 to the 25th, and that's molecules of CH4. And make sure you have the proper units and the proper element or compound in your answer, along with significant figures so you don't get points taken off. All right. Let's do the other problem I mentioned, 280 moles of gold. Okay, and remember, gold is AU. And so I know gold is just one element, so that means I'm going to atoms, which I put at the top, and I want to get rid of moles, so 1 mole of gold at the bottom. I still use Avogadro's number for this, so 6.02 times 10 to the 23rd. Moles are going to cancel out, and I just plug it into my calculator. 280 times 6.02 times 10 to the 23rd. Right arrow, close parentheses, divide it by 1. I'm left with 1.6856 times 10 to the 26th, but I had 2 significant figures here, so I'm going to report my answer in 2 significant figures. 1.7 times 10 to the 26th atoms of gold. Okay, so if I was asking for you to go in reverse, and there are some problems on this unit sheet that help you go in reverse, so to speak. 3.01 times 10 to the 23rd atoms of titanium, and it wants you to go to moles. And this is the same process. You are just flipping your conversion factor, or your conversion fraction, as some people call it. So atoms of titanium. So we know this is our conversion factor. And so what we're going to do is we're just going to flip it. I want moles, so I'm going to put that 1 mole on the top now of titanium. And I am going to put 6.02 times 10 to the 23rd, and this is atoms because we're working with 1 element at the bottom. Atoms are going to cancel out, and so this is where that fraction button comes in handy. Okay. Hit ND, and I put in parentheses 3.01 times 10 to the 23rd, hit over, close parentheses, divide it by 6.02 times 10 to the 23rd, and we are left with 0.5, but I had 3 significant figures, so I'm just going to put 0.50 moles of titanium as my answer. So that is my simple one-step problem. Okay? So hopefully those one-step problems are not an issue here. And so there's a bunch of practice. Here's your grams to moles, moles to grams, and moles to atoms, moles to molecules, and then atoms and molecules back to moles. Use these as practice. Stop the video now if you need more practice. But now what we're going to do is we are going to look at 2-step problems that combine the 2 techniques that I have just shown you. Remember, we cannot just go from grams to atoms straight. We have to go through the mole first because this is the only relationship that brings them together. It's just like saying if I only gave you the conversion factor that 1 inch equals 2.54 centimeters, okay, and I told you I want you to take 3 miles and convert it to centimeters, you're not going to take a direct path here because you don't really know a direct path there. So you're going to have to use what you know. Go from miles to feet, feet to inches, and then you can finally go to centimeters. And that's the technique we use here with moles. We can't go from atoms to grams straight. There's not a conversion factor you know directly. So we have to convert to moles first using what we know, and then finally convert to grams. Excuse that bell. I don't know if they're fixing it or what, but we're just going to have to work through it. So if you look at this paper, I have 264 grams of water, and it wants us to go to molecules. So this is a two-step problem. I have 264 grams of H2O, and I want to go all the way to molecules. So I'm going to draw this large line. This is also a way that I write it. Okay, this just means multiply, this just means divide, and it keeps everything separate and a little bit cleaner for me. So I know in order to go from grams to moles, I have to use the periodic table. So I have to find the formula mass of H2O, and I'm going to do my scratch work down here. I have two hydrogen atoms, which has a 1.01 mass, plus oxygen, which has a 16 gram mass. And so then when I put it together, I get 18.02 grams, and then I want to look at the molar mass because that shows us the relationship, so it's grams per 1 mole. So I have to convert to moles first, so I will put this 1 mole of H2O at the top, and I will put this 18.02 grams of H2O at the bottom. And I know I'm where I want to be because grams are going to cancel out. Alright, but I'm not done because I want to go to molecules. So I know I can do that by changing 1 mole of H2O into molecules by using Avogadro's number. So 6.02 times 10 to the 23rd. Moles will cancel out, and now I'm finally in the unit that I want to be in. So I'm going to hit my ND button, and I'm going to type in 264 times 1 times 6.02 times 10 to the 23rd, and then I'm going to divide it by 18.02 times 1, and I'm going to get 8.82 times 10 to the 24th, and that's molecules of H2O. And make sure you write molecules out. You cannot use some type of abbreviation, because if not, it makes it look like moles or it makes it look like molarity, which we haven't got to yet. Okay, so that's a two-step problem, and we can always work backwards. Let's look at this sheet again. I can see I have atoms, and I want to go to grams instead. So let's look at this number 49, 7.5 times 10 to the 19th atoms of sodium. Okay, so we always start with what they give us at the top left. And I know to get to grams, I have to go to moles first. So what conversion factor do I know that we can use to get to moles? Well, we know that 1 mole is equivalent to 6.02 times 10 to the 23rd. And I always love the step between atoms or molecules and formula units to moles, because it's just this number. We do not have to multiply by subscripts. We don't have to change anything about it. This is always going to be the conversion factor we use. And so atoms will cancel out, and I'm left with moles. And then I know I want grams last. So I'm going to put grams of sodium right here at the top, and I'm going to put 1 mole down here at the bottom. And so moles will cancel out. And remember, nothing other than 1 is going to go with moles right now because we are looking at these simple conversion factors. Well, I know sodium's mass, or molar mass on the periodic table, is 22.99 grams per 1 mole. So finally, I'm in the unit that I want. So I'm going to plug in my calculator now. I'm going to put 7.5 times 10 to the 19th power times 1 times 22.99 divided by 6.02 times 10 to the 23rd. And and we get 0.00286. You can either stick this in scientific notation to help significant figures be a little bit cleaner, or you can round to two significant figures, so it would be 0.0029, and that's grams of sodium. And so that is the opposite of what we just did with our two-step problem. So you can go from grams to atoms or molecules or formula units, or go from atoms, formula units, and molecules back to grams. Okay? Now, as far as our other single conversion goes, we mostly use it when we are looking at gas law. So we don't really talk about it too much in here, but if you look at our lecture slides, you will see it at the bottom of your notes. And so I'm just going to show you one simple conversion. Okay, I have, let's see, I have 100 liters of hydrogen. And remember, we're going to put hydrogen, it is diatomic, down here, and I want to know how many moles this is. Well, same thing when we're going from moles to atoms or atoms to moles. We don't have to take into consideration the subscript number here. We just use 1 mole is equivalent to 22.4 liters of hydrogen. And so what happens is liters cancels out, and I'm left with moles. And so we take 100 divided by 22.4, and I have 1 sig fig here, so I round up to 5 moles of H2, or hydrogen, right there. And that one-step conversion is also very simple. We will maybe have 1 or 2 questions over that right now, but the rest we will save for gas laws in a few weeks. Right, so hopefully this helped clarify some things with the mole for you. Definitely use this sheet. Down here are our two-step conversions or dimensional analysis problems using the mole. So take a pause, look at these, and if you have any questions, just let me know.